Good afternoon, Rich Nass, Executive Vice President with Open Systems Media, here for another presentation at the Automotive Technologies Virtual Conference. This presentation is titled Keep Automotive Device Data Safe. And I think there's something else at the end of that, but I'll have Thom talk about that. The speaker is Thom Denholm. He is a technical product manager with Tuxera. Hello, Thom. How are you?
Hey, Rich. Very good. Thank you.
I added the title of your presentation. What's the proper title?
It's keeping device data safe with secure erase.
There you go. I lopped off those last two words. I apologize. So what can somebody expect to learn from your presentation?
So embedded devices today, and automotive devices are embedded devices inherently, are used to store a pretty wide variety of data. And some of that data is secure. Okay, so it can be encrypted, it could be encoded, but when we remove that data is supposed to be gone. The system designer expects it to be gone. And so in this conference, what I really want to talk about is how to remove the data securely, how to remove it once and for all. Okay, so there's no lasting security through obscurity. So what does it mean to remove data? Why is NAND different from the past media? So we'll give a quick intro to that. And then we'll talk about secure data on NAND and ultimately the hidden cost of removing that data. We'll then examine the layers of an embedded design or automotive design, all the different interfaces that can be used to deal with that secure data in NAND-based devices like eMMC and SSDs, and how the file system needs to deal with that. And then finally, what an application can do to make this easier and effective. And then my final thoughts. Proper security is a process, encompasses the design of the entire system. Neglecting that process will lead to suboptimal data removal and increase the risk of sensitive data falling into the wrong hands, and in many cases, greatly reduce the lifetime of the device. So what does data removal mean? Well, let's start with data removal through history. Data etched in stone can be defaced. Data on clay tablets can be crumbled. More recently, data on paper can be burned or shredded. Data on magnetic tapes can be erased, especially 18 minutes of incriminating data. Or can it? So on magnetic media, a simple erase was shown to be ineffective, leaving remnants behind. We used a technique called scanning probe microscopy, and we were able to find those remnants with really high resolution. To allow more storage and lower prices, media vendors use shortcuts like multiplex and run length limited encoding, also known as RLL. These tricks ultimately made recovery of that data easier, and we'll come back to those shortcuts in the NAND section. In the case of the Nixon tapes, overwrite of the data proved somewhat effective, if a bit incriminating. In the decades we've had magnetic media, many people have studied how to remove that secure data. Full erasure involves an erase, an overwrite with a complement, and other strategies. Government and military specifications document these requirements today, but are they appropriate for NAND? All of you have probably heard of NAND Flash. Many of you maybe already know how it works. So bear with me while I give a brief overview, and then I'll transition into how that limits us for secure removal of the data. This is a really abstract view of NAND media with two important objects, the write page and the erase block. The minimum size you can erase is an entire erase block. I won't go into the circuit level details, but this is a really slow process, and we'll come back to that soon. The size of an erase block is dependent on your media, but 128K bytes is a good starting point. The minimum size you can write is a full write page. Again, the size of that write page varies with the overall size of the media, but 2K bytes is a pretty good start. This write page can't be overwritten or appended to. When an application writes a few hundred bytes, the NAND needs to write that full 2K or so. Any update means replacing it with a new one and then marking the original one as obsolete. This is known as copy on write. Both those processes are pretty straightforward and very public facing. Another one is less well known, and that's compaction or garbage collection. When the data on several of those write pages is marked obsolete, the remaining write pages with good data are copied to free locations. Each of them are now marked obsolete so that a later erase can clear up the entire erase blocks. This compaction takes place in the firmware of drives like eMMC, SSD, and SD cards. Our company provides a software flash translation layer for nearly 30 years. So I'm speaking from a lot of experience. We didn't write the firmware for the MMC, but we've written software which does exactly the same thing. So really the question is, which write pages can have secure data on them? Well, the originals of write pages that were updated, the originals of write pages where the data which was secure was copied elsewhere, waiting for compaction. Any situation with a secure data in an erase block which hasn't been erased yet. And of course, every live page that still has secure data on it. There's other situations like static wear leveling that could cause copies of that secure data. And the internals of the NAND firmware are not available to the rest of us. So I'll only speculate on other situations. But really the question is, why are there so many copies of the secure data? Like previously, this is another shortcut. This time it's for performance. NAND is quite slow to erase. I mentioned that earlier. Usually extra erase blocks are available, hidden from the user, so the erase can happen in idle time. The throughput values on the vendor data sheets take this into account. Now, to meet the goal of security, secure data really needs to be erased immediately, even if the erase block isn't fully written. You may have heard of write amplification, which increases the amount of data written. This is like an erase amplification. It reduces the amount of data that can be written to the device. The lifetime is measured in program and erase cycles. So this is less of a problem for a few keys, but if you have a database with a lot of secure data scattered over, it can really impact the device lifetime. Obviously, erasing immediately also slows the performance. Ultimately, embedded designers can have security or speed, but not both. NAND media connects to the embedded design through a variety of interfaces and drivers, and that includes connections to the NAND chips too. NAND-based media needs software to manage it, to handle that wear leveling, and that's often provided in firmware. As previously noted, the firmware is not available to read for most of us, so you can get the specifics from your flash vendor, and you should definitely check those specifics if you make a bill of materials change to a different vendor. JEDEC, the committee, manages eMMC, so I'd like to start with that as an example. JEDEC specifications 4.5 and earlier provided a secure erase command to augment the standard erase command for secure data. I don't know how it worked internally, and probably that varied from vendor to vendor, whether it forced an immediate compaction or it merely marked the page as removed, but it did give a direct level of control to remove the secure data. In fact, we adapted our file system, Reliance Nitro, to provide a secure delete, which matched up with that secure erase directly. In newer versions of the specification, they marked this command as obsolete and replaced it with something called sanitize. Instead of removing a single secure page, the sanitize command removes all of the pending pages, whether or not they contain secure data. As you can imagine, on a system with a lot of write page changes, this command can take quite a while to complete. Partly as a way of dealing with that delay, JEDEC added a secure removal type to the specification. This way, vendors can provide options for their customers. I think you'll recognize a few old friends here. The extended CSD register can be used not only to set the secure removal type, but also to get the potential types that are available. Here are some of those options. Bit 0 is what I just described, where the page and block is erased immediately, whatever the time cost. That's also the default. If you set bit 1, that removes the information, overwrites the block, and then erases that. Bit 2 removes, overwrites, and erases, overwrites with the complement and erases, and then overwrites with a random character and erases. Well, we saw that earlier, the old magnetic media erase techniques. Were these added because they were effective on NAND media, or were they added to comply with government or military regulations? I suspect the latter. What I can say is using these operations on media with a lot of erase blocks to sanitize will again seriously impact the program and erase counts and shrink the life of that media. Bit 3 specifies a vendor-defined method. Again, reach out to your vendor. One vendor we work with defines Bit 3 operation as clearing the physical to logical address table. As an analogy, this is kind of like removing the shelf tags in a library while leaving the books. The secure information is still there. It's just not as easy to get to. Ultimately, you want to have a conversation with both your customer and your vendor to make sure that your requirements are being met. I'm not a lawyer. I'm not even a cat. I cannot advise you on this process. eMMC and UFS use firmware on the chip, which we've been talking about. FlashFix Terra is a product we make that's a raw flash with a software controller and allows you full control over secure erase and complications. There's other forms of NAND-based media as well. SSDs connecting over SATA or eSATA may be able to use the ATA secure erase command if it's provided by the vendor. My research shows that this command is for drive-wide use. It erases the entire media and restores it to essentially factory default settings. So this is really good for a use case of transferring the device to a new user, but not really good for removing a few files with secure data. It sounds like a broken record here, but talk to your media vendor. SD cards don't support either one of these interfaces. There's no way to directly remove secure data on this very popular medium. Being a removable and portable format, I'm sure that securely removing data wasn't in the planned use case. The SD Association is looking at other less removable form factors coming soon, and Tuxera plans to encourage them to adopt secure erase techniques for those designs. We're a member of the board of directors. That said, there are downloadable utilities for securely erasing an SD, which seem to follow the magnetic media clearing model with the overwrites and the complements. They don't have low-level access to the individual blocks. None of the READMEs and other documentation of these utilities mentions anything I've covered here. So I think that these types of utilities would both shorten the life of your media and not actually remove any secure data, which is really not the best outcome. Before I move on to the file system, I'll conclude that in order to securely remove data, the firmware has to be able to directly address the NAND and exercise the control over normal erase and compaction. So the file system interface, well, NAND is more than just a simple block device. File systems deal with the media using read, write, and erase. When a file system overwrites a sector, the NAND will be able to write the data to a new page. Remember, there's no overwrite possible, and the original data is marked as no longer in use by that firmware or software. When a file system erases the data, what happens next is based on an additional interface known as discard or trim. This command allows the file system to notify the media when a write page or a block device sector is no longer in use. Until the file system notifies the media, the data is considered valid, and the sanitize command we talked about earlier will not remove that data. Mounting a drive with discard or trim enabled is done with this option on Linux, though your file system choice might vary. When this command is enabled, each erase is followed by a discard. In some use cases, this can really slow the performance of the media. If you're dealing with a lot of small files, discarding after each one can effectively double the workload and possibly shorten the life of the media. This is also known as automatic trim. Another command acts as a manual trim, and that's FS trim. This command can be called infrequently, where it will discard all the deleted blocks. Grouping multiple discards together will provide better performance, but on the other hand, any firmware option that happens before the FS trim is called will treat the deleted data as valid. So in other words, it's a trade-off. The small performance hit for the automatic trim using this command here is why Linux file systems have the discard option disabled by default. And that's a bad idea, frankly. To measure just how bad, we performed a series of write and erase pairs with discard disabled, okay, to measure the write performance, the throughput of the drive. Once the entire media, in this case, this is about an 8 gigabyte part, was used once, each subsequent write required an invisible erase at the firmware level, and the write performance dropped precipitously. You can bet that the higher performance is what was shown on the datasheet. Utilizing a smart discard or a regular FS trim allows the design to clean up during idle time. If your use case has that and will end up with a consistently high performance over the life of the device, not just that first 8 gigabytes. So now we've talked about the flash media interface and the file system. Let's go a little higher to the application. What can the application do? It doesn't have access to the media discard interface. It can choose how frequently FS trim is called. Calling FS trim during idle time removes discarded pages and shortens the required time for the sanitize. Even if you didn't have access to FS trim, a file system can overwrite the secure data first. As we covered, the NAND is not truly overwritten, but the data from the previous write page will be marked as obsolete internally by the flash media management without any file system intervention. Keeping the secure data together in a manageable location will also minimize the impact on the media. While a database may be convenient for your use case, the secure data in a database and the possible backup copy may be scattered around a wide variety of locations. The best solution would be to bring your concerns to the database vendor and discuss it with them for the best possible solution. So, in closing, the biggest problem with mishandling secure data isn't a problem if the device doesn't fall into the wrong hands. The second biggest problem is dealing with the secure data improperly, which we've shown reduces the lifetime of the flash media. Both of those fall under added cost. So ultimately doing things the right way is a cost savings. Besides the direct user experience of the data in the wrong hands, handling secure erase properly means a more responsive device and less downtime. Coming back to where we started, secure data removal is the result of a process, including discussion with your vendors and planning the best handling by the file system and the application. We provide file systems and flash management software. So this is a discussion I've had with many potential and current customers. This conference doesn't have a direct Q&A section, but I'd be happy to answer any questions you might have. This is my contact information. I'll be available here on the platform for any other questions, and I'll be available right around the same time that this is presented. As the primary author of white papers for Tuxera, I can also direct you to other informative resources on file systems and flash management. Thank you.
Well, thank you, Thom. That was very informative. The first thing that comes into my head, though, and obviously I'm not an expert in this technology, but what you're talking about seems very basic. The why you'd want to do this and how you do it. Is it not that as easy as it should be or seems to be?
The real problem is that the interfaces are somewhat hidden. The direct access to the secure data is not there. And so you have to jump through a hoop or two. And if you don't know where those hoops are, you kind of make an assumption that, well, everything below me is working right. It's going to take care of it for me. Well, that's not necessarily the case. Having this extra knowledge, being able to step through and do things the proper way, calling an FS trim, for instance, can allow you, even at the application level, to control what's going on below you.
And you showed some examples of the performance where you were showing those performances. I'm assuming that those are worst case.
That was an average case over several, unfortunately. So yeah, I imagine that the firmware on some of those devices does some of that cleanup and trim in the background, which is why you don't see the performance drop as largely as we did. We didn't allow it any kind of dwell time, any kind of idle time. We hit it pretty hard. But then again, your use case might require constant usage. And if it does with constant writes, you'll see this same sort of performance drop.
Okay, very good. Well, you saw how to contact Thom if you do have other questions. I certainly encourage you to check out all the other presentations. They are in this track, which is security. We also talked about how to power the electric vehicle, autonomous drive, IVI, and infotainment.